Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. So students, today we are going to discuss about the module, a review of chemical bonding in materials from the paper Functional Materials. The main points which will be covered in this module are: first, classification of materials on the basis of their bonding and physical characteristics will be discussed in this module. Second, materials can also be classified as metals, semiconductors, and insulators based on their electrical characteristics. Third, according to the magnitude of their bond energy, the bonding in the materials can be categorized into primary bonding and secondary bonding. Fourth, there are three types of bonding, mainly primary bonding mechanisms, that is metallic, covalent, and ionic, will be discussed in this module. Lastly, we will discuss about the secondary bonding due to permanent dipoles. So students, let us start with a brief introduction about the module. The properties and the behavior of materials is largely determined by the nature of chemical bonding between the atoms. Bonding arises because of electrostatic interaction between the atoms due to the presence of positive and negative charges in such a fashion so that any material system assumes a lowest energy state in equilibrium. As we will see, bonding can also be a defining parameter for the type of materials. These characteristics are reviewed in the subsequent sections. Materials classification. Scientifically speaking, materials can be classified on the basis of their bonding and physical characteristics, and that are again determined by which particular functionality we are interested in. From the mechanical characteristics perspective, we divide broadly materials into four categories. First is metal, which includes all the alloys. Second is ceramic, which includes all the glasses. Polymers, including elastomers. And lastly is a composite. Materials property charts, as shown in the figure, which typically describes the basis of strength of weight ratio of the materials. Here one can see that most metals belong to high density and moderate modulus category, whilst ceramics are the materials with higher modulus but lesser density. On the other hand, polymers have relatively very low density as well as modulus. Similarly, based on the electrical characteristics of materials,
One can classify them into the following categories. First, metals having high electrical conductivity, that is, conductivity is exceeding 100 S per centimeter. Second is semiconductors, moderate or low electrical conductivity. Finally, the insulators having very low electrical conductivity. However, one crucial factor that imparts these materials such character is the nature of bonding between the constituent atoms and the way the atoms arrange themselves in space. So, first, we will spend a little time on reviewing these fundamentals.
So, students, let us discuss about the classification of materials based on their electrical properties. So, we can classify the materials into three categories. First is a metal having high electrical conductivity exceeding 100 Siemens per centimeter. Second is a semiconductor having moderate or lower conductivity between 1000 to 10 to the power minus 8 Siemens per centimeter. Third is the insulator having very low electrical conductivity below 10 to the power minus 8 S per centimeter. Bonding determines the material's behavior and its properties.
Interatomic forces and potential energy. When the two atoms are brought together, the force between the two varies as a function of their separation r and can be plotted as shown in the figure. When the separation is large, there is a net attractive force between the atoms, which is dominated by Fa, that is negative, and when the separation is small, the atoms repel each other, which is dominated by Fr, which is positive. When the atoms are closer, the repulsive forces are high due to repulsion between the outer shell electrons of the two atoms, and when the atoms are taken further away, they drop very rapidly. At a distance r0, as shown in the figure, these forces cancel each other, and this is called as the equilibrium separation between the atoms. At this distance, as we can see from the figure, the potential energy of the system becomes minimum. The overall potential energy of such a system is represented by the Lennard-Jones potential, that is, W as a function of R is equal to 4 epsilon multiplied by sigma by R to the power of 12 minus sigma by R to the power of 6. This is also equivalent to minus A by R to the power 6, that is the attractive force, plus B by R to the power 12, that is the repulsive force. Here, your left hand side represents the attractive force and the right hand side represents the force due to repulsion. That is the negative due to attraction and the positive due to repulsion. The energy corresponding to the equilibrium separation is called as the bond energy of the materials, which is typically expressed as kilojoules per mole or electron volts per bond. It is the magnitude of this energy which is quite informative vis-a-vis materials' properties and the nature of bonding between them. In general, higher the bond energy is, higher would be the melting point, elastic modulus, and hardness, and lesser is the coefficient of thermal expansion. Accordingly, the magnitude of bond energy, the bonding in materials can be divided into two categories. First is primary bonding, second is secondary bonding. Primary bonding exhibits the bond energies in the range of 50 to 1000 kilojoules per mole. Primary bonding are metallic, covalent, and ionic bonds, with metallic bond typically being the weakest. On the other hand, bonds with energies lower than the 50 kilojoules per mole are called as secondary bonds, and the examples of secondary bonds are van der Waals bonds and the hydrogen bond. These type of bonding will be discussing in the preceding sections. First type of primary bonding which we'll be discussing now is the ionic bonding. The electrons transfer from one ion takes place to the other ion. Higher the difference between the tendency to accept and give away the electrons, described by the difference in the electronegativity of the two ions, stronger the bond will be, due to spherical symmetry of atoms and thus the bonding force around the atoms. Ionic bonding is non-directional in nature. To begin with, the ions can be treated as point charges, and when the two charges are brought closer to each other, the attractive force between the two can be written by Coulomb's law, that is minus A q1 q2 by r square, where A is a constant and q1 and q2 are the charges on each ion and r is the separation distance. The resulting potential energy can be written as minus A q1 q2 by r. This attractive force varies as the square of the distance between the two ions. However, when the atoms are brought too close to each other, their electron clouds start overlapping. Since Pauli's exclusion principle cannot be violated, as no two electrons can occupy the same quantum state, this leads to the development of a repulsive force between the ions, which increases very sharply with the separation distance. The repulsive energy is expressed as B divided by r to the power m, where B and m are the constants which are determined empirically. Thus, the total potential energy of the system can now be expressed as W is equal to minus A q1 q2 by r plus B by r to the power m plus delta E, where delta E is the difference between the ionization potential of cations and electron affinity of the anions and is typically a very small number. The bond energy is determined by taking delta W by delta R equal to 0, yielding an equilibrium bond energy delta naught at an equilibrium distance of R naught. As the above expression shows, and also true in general, the higher the valence of the ions, the bonding is typically stronger. The examples of ionic bonding. This type of bonding leads to high bond energies, and as a consequence, ionically bonded materials typically exhibit high bond strength, high melting point, high elastic modulus, brittle nature, and generally low thermal and electrical conductivities, making them excellent insulators. Typically, bond energies in these materials exceed 100 kilojoules per mole. This bonding occurs between two oppositely charged elements, for example, in NaCl, MgO, zinc oxide, lithium fluoride, and many other ceramics and glasses. Next type of primary bonding which we are discussing now is covalent bonding. In this bonding, atoms share their outer shell unpaired electrons, leading to a stronger and directional bonding, as shown in the figure. An overlapping of the orbitals is required for lowering of potential energy, which is typically facilitated by the vacant states in the outermost orbital of bonding atoms. Typically, overlapping orbitals are directionally oriented, which further gets compounded by hybridization between overlapping orbitals, imparting a strongly director character to covalent bonds. For example, 2s and 2p orbitals in carbon form sp3 hybridization, which can hold a total of 8 electrons and facilitate the sharing between the neighboring carbon atoms in such a fashion that each carbon atom is surrounded by 4 carbon atoms in a tetrahedral coordination, forming a regular tetrahedron. This leads to inter-bond angle of 109.5 degree and a strong directionality in diamond. The examples of covalent bonding. The examples of the materials showing this type of bonding are primarily from group 4 and 5 elements, and the compounds such as silicon, carbon, germanium, and silicon carbide, nitrogen, phosphorus, arsenic, antimony, and bismuth. The bond energies of some of the common covalently bonded materials are 176 kilojoules per mole for silicon and 347 kilojoules per mole for diamond. The last type of primary bonding is metallic bonding. Metallic bonding is characterized by the presence of a sea of electrons around atoms in metals, also called as free electron gas. The sharing of electrons is not complete enough to provide a covalent character and is delocalized. This very nature allows free movement of electrons around the metal cores whilst holding the cores together. This nature gives rise to flexible bonds, good malleability, high electrical and thermal conductivity. Typically, most elements to left of fourth column in periodic table shows such a kind of behavior. Examples of good metals are nickel, iron, copper, gold, silver, etc., and their alloys. Most metals shows a bond energy below 100 kilojoules per mole, which is a moderate energy. This is why most metals have moderate melting points, moderate elastic modulus, and moderate coefficient of thermal expansion. Now, students, we will be discussing about the secondary bonding. Secondary bonding arises from the interaction between the charged dipoles. The magnitude of this bonding is typically below 50 kilojoules per mole and even lower. First kind is of between fluctuating dipoles. It is observed in gases like hydrogen as shown in the figure. Second type is induced by the existence of permanent dipole moment induced due to the presence of permanent dipoles in the materials such as on polymers, where within a chain units are covalently bonded, while between two chains secondary bonding exists. Typical example of materials and their bond energies showing secondary bonding are water, having bond energy of around 20.5 kilojoules per mole, ammonia, having energy of around 7.8 kilojoules per mole, and HF having energy of around 31.5 kilojoules per mole. Although in above paragraphs we have defined particular type of bonding, in reality most of the materials shows mixed bonding. Nevertheless, the materials are defined by the dominant type of bonding in them. This classification is useful in approximately classifying their properties and behavior under a given set of conditions. Also, the length of a bond is defined as the distance between the centers of two atoms. The materials with stronger bonds typically have stronger bond length, that is below 2 angstrom, due to high attractive forces. In contrast, secondary bond lengths are typically longer, of the order of 2 to 5 angstrom, although half of the bond length is often taken as the diameter of an atom. If the two atoms are same, it is often determined by the constraints of packing, and coordination number. In this slide, this table summarizes the typical differences in the bonding in different materials, which can lead to vast changes in their physical properties. First type of bonding is ionic, having a very large bond energy, and it is non-directional. Second type is covalent, having variable bond energy and is directional. Next is metallic bonding. It is also having variable bond energy and is non-directional, occurs in metals. The fourth kind of bonding is secondary bonding, having smallest bond energy and it is directional, that is interchain for the polymers and intermolecular.
So, students, let us summarize what we have learned from this module. We have categorized the materials based on their bonding, and the first category is ceramic, having ionic and covalent bonding, and the bond energy is very large, and they have a large energy and Tm value and a small alpha. Next type of bonding is a metallic bonding exhibited by metals. They have a variable bonding energy, a moderate value of Tm, moderate energy, and a moderate alpha. Third type of bonding is a covalent and secondary bonding exhibited by the polymers. They have directional properties, and the secondary bonding dominates over the covalent bonding. They have small t, small e, and large alpha. Next type of categorization which we have discussed is upon the bond energy. First is ionic, having very large bond energy. It is non-directional and it is exhibited by ceramics. Second is covalent, having variable, that is diamond is having largest and bismuth is having smallest. It is directional and it is exhibited by semiconductors, ceramics, and polymer chains. Third is metallic, The smallest is mercury, and tungsten is by the having the largest bond energy. It is non-directional, exhibited by metals. Finally, we have a secondary bonding which is exhibited by the polymers and intermolecular, and it is directional. Thank you.